All right, so we're just going to kind of do a quick overview of the first two sections, 4.1 and 4.2. We're going to be talking about triangles, some names and ways we can classify triangles, symbols that were used, stuff like that, and also some of the angle relationships and theorems that are present in triangles. So for our objectives here, basically we want to be able to classify triangles by angles or sides. Use the triangle sum theorem to find the measures of the third angle. We're going to throw these in there. There's some more stuff we're going to get at, like the specific notation that's used with triangles and other stuff along those lines. So first of all, we have our triangle ABC. The sides of a triangle are segments. Now, obviously, these segments could extend and be parts of lines or rays, but the part that is a triangle is a segment. So segment AB, segment BC, segment AC. Those are the sides of our triangle. A, B, and C, we call these vertices. That's plural. Each one of them would be called a vertex. And also, these are our angles, right, of our triangle. So angle A, angle B, angle C. The way that we name triangles are using the vertices or angles and the symbol for a triangle here. So some options for the name of our triangle here could be triangle ABC. We pick one of the vertices and then we just kind of go around the outside. So ABC, we could also call it BCA or CAB or BAC. There's probably a couple more in there. Anyway, any of these would be appropriate names for the triangle. All right, so quick reminder, we did a proof of this in chapter 3, but it's called the triangle sum theorem. And the basic ideas of the triangle sum theorem are that the three angles of a triangle, so in this case, angle A, B, and C, all add up to 180 degrees. Now, this is based on the parallel postulate and using alternate interior angles. Basically, the parallel postulate guarantees that if we pick one side, we can always draw a line that is parallel to that side through the other vertex. So I drew this line that was parallel to this side through that vertex. We know these always have to add up to 180 because that's the definition of a straight line or a straight angle. And then using alternate interior angles, it's easy for us to see that angle A is the same as that one. Angle B, that's part of our triangle right there. And then angle C, this would be the same as this one, again, by alternate interior angles. So all of those angles, A, B, and C, can be represented up here, making a straight line, thus equaling 180. And that's the basic idea of the proof. We'll kind of take a look at it later on, just to kind of remember that. But what we really need to know and what we'll be using a lot is all three angles of the triangle add up to 180. That's going to be really useful when we know two of them to find the third. All right. So classifying triangles, one way we can classify a triangle is by its angle measurements. So an acute triangle has 3 acute angles, meaning all of the angles are less than 90 degrees. So less than 90 degrees. That's what we mean by acute. An equiangular triangle means all 3 angles are congruent. In that case, they're actually 60-degree angles. We'll talk about that later. A right triangle where we have one right angle. The others can't be 90. They would actually be acute in this case. One right angle makes it a right triangle. And an obtuse angle means we have one angle that is obtuse, which means that it's greater than 90 degrees. Greater than 90 degrees. That's what we're talking about when we say obtuse. Okay. So that's classifying a triangle by its angle measurements. So let's take a look at this example. Let's go ahead and try to classify each of these triangles here by the angle measurements. So as we go through this, I'm going to kind of highlight what triangle we're talking about. So the first one is EHG. So EHG. That means those are the vertices of my triangle. So I'll go ahead and connect those. So this is the one we're talking about. And our angles here are 30 degrees at angle E, 60 degrees at G. That's a different one, so I'll mark it there. And then H, I mean, technically we shouldn't call this H because there's a couple angles here. So this one would be angle maybe EHG. EHG, right? That makes that 90-degree angle. So this one has a 90-degree angle. So that makes this one a right triangle. Right? One 90-degree angle makes it a right triangle. Okay, and then let's go ahead and take a look at the next one. HFG. So HFG. So those are our vertices there. So in this case, we have two 60-degree angles. Using our triangle sum theorem, we know these three have to actually add up to 180. So 60 plus 60 gives us 120 degrees. So if we take away 120 degrees from what is known, right? We know that they have to add up to 180. That means there are 60 degrees left for that final angle right there. A couple other ways we can come up with that, but that's fine. So in this case, we have all three that are 60-degree angles. That makes this one most specifically an equiangular triangle. All the angles are equal, but it could also be called an acute triangle, right? Because all of these are less than 90 degrees. All right, and then our last one, HEF. So HEF. All right, so similar situation here. We know two of the angles, but we're missing this last one here that's at F, or I guess this angle more accurately would be EFH, because we couldn't call it just F because that's ambiguous between which of these we're talking about. But anyway, we know two of them, so that's 30 degrees and 30 degrees. So that is 60 degrees of a total of 180 we need here. So if we do 180 minus 60, that should give us what's left, which is 120 degrees. So that makes this one an obtuse triangle because we have an obtuse angle, right? Yep, obtuse triangle. All right, so classifying by angle measurement is one way to do it. The other way to do it is by side length. And we'll actually throw those two things together sometimes as well. But so we have three side length classifications. So we have an equilateral triangle where we have three congruent sides. All the sides are equal. Isosceles, where two of the sides are equal, or at least two. And scalene, where none of the sides are congruent. All right, so let's classify each of these triangles by their side lengths. So we have triangle A, B, C. So that's this one right here. Those are our vertices. We have one of the sides marked at 15 and a congruent marking over here. So this one is 15, this one is 15, and the bottom is 15. All of them are the same, they're equal, so this is an equilateral triangle. All right, and then the next one, we have triangle DAB. So it's actually this largest triangle here, DAB. In this case, we have a side that is 15, a side that is 18, and a side that is 20. So none of these sides are equal at all. So that makes this one a scalene triangle. We didn't have a isosceles in here, although this triangle ABC, our first one, could be called isosceles, but that would not be the most appropriate name for it. All right. All right, so the next thing we want to talk about are some angle relationships in triangles. So we have the triangle sum theorem, which we just talked about. This one is really important. Used all the time to find angles inside of triangles. So all the angles of a triangle will always add up to 180. Doesn't matter what kind of triangle we're talking about. Any of the types for scalene, equiangular, equilateral, isosceles, acute, obtuse, right, all of them will have this same sum. It's really useful. We're going to take a look at a proof of this theorem, and we'll be using it a fair amount. All right, so here is a proof. So the only thing that we are given here is just some triangle. The key to this is kind of what I was mentioning before. Uh, there's a postulate in geometry that says we can always draw a line that is parallel to another line through a given point. So we're going to try to show that the measures of these three angles, 1, 2, and 3, all add up to 180. So first thing we do is we draw a line that is parallel to one of the sides through the other vertex. So that's right here. Went ahead and drew that line. Now, what that does, that creates some parallel lines here and here. Thus, we can use our alternate interior angles theorem. So we can say that angle 1 and 4 are equal. Right there, that's what we're saying that. And we can say that angles 5 and 3 would also be equal again. They are alternate interior angles. They're between the parallel lines in the interior space and on different sides of this transversal, or on different sides of this transversal, depending on which angle pair we're looking at. So we know those angle measurements are equal. That's what this next step is telling us. Since the angles are congruent, the measures of the angles are equal. Now, we said before, earlier, that anytime we have a straight line, we know that creates a straight angle. So right here, these three angles create a straight line. So using the definition of a straight angle, knowing that it measures 180 degrees, and the angle addition postulate, so adding them all together, angle 4 plus angle 2 plus angle 5, we know that those have to equal 180 together. Now, taking this equation, a little bit of substitution, we can replace angle 4 with the measurement of angle 1 because they are equal. We can replace the measurement of angle 5 with the measurement of angle 3, again, because they are equal, thus giving us the result we want to do, that the three interior angles of our triangle have to add up to 180. Now, this is a proof of the general theorem. Doesn't matter what shape this triangle is. We didn't say any of these angles were any specific measurement at all. This happens to appear to be an acute triangle, but it doesn't matter. The same proof works no matter what our original triangle works with. All three angles will always add up to 180. All right, so then we have a couple corollaries based on that. So the first one is, a corollary is a theorem that directly follows from another one. Usually it means that it's a specific case or a specific condition of that previous theorem. So the first one is a specific condition of the triangle sum theorem when we're dealing with a right triangle. When we have a right triangle, since we know one of them is 90, these other two have to add together to be 90, because 90 plus 90 is 180. So that means that these are complementary angles. So when you have a right triangle, the non-right angles, the acute angles, have to be complementary. They have to add up to 90. Because, again, they all have to add up to 180. If we're already accounting for 90 degrees of that right here, then these two have to make up 90 together. So it doesn't matter what they are. They could be 60 and 30, 80 and 10, 20 and 70, some other combination that adds up to 90, but they do have to add to 90 degrees. So again, it's a specific case when we're dealing with a right triangle, how the triangle sum theorem is going to work, which makes it a corollary. We could call it a theorem too. We're not going to necessarily use it, but it's worth talking about. Next one, the measure of each angle in an equiangular triangle is 60. This is pretty easy. If we know a triangle is equiangular, again, this is a specific case of the triangle sum theorem, we know that all the angles are equal, so we could easily just call them all x. Well, if we add those all together, they would have to equal 180, right? X plus x plus x is 3x. Divide by 3, we end up with each angle equaling 60 degrees. Pretty simple case, and we can check that. Yeah, 60 plus 60 plus 60 does add up to 180. Fair enough. They're just some really specific results that are based on the triangle sum theorem. And that's really all we need to know going into this. See you guys later and have a good evening.